There's about 10 miles or so in between Minneapolis and St. Paul. And where my drone is about 25 miles north of Minneapolis. So that's what the buildings look like from 25 miles away. So when we zoom back out and we see our 10 miles, and if we add up just on the screen here from left to right, it's about 100 miles. But that's at that 25 mile distance that it's about 10 miles. And we can see beyond some of that. So when we see our 10 miles from here to here, when we zoom out, it's about 100 miles. Now, one could argue that it could be far more than 100 miles left to right. But we have actual physical objects giving us approximate distances about 25 miles away. So at about 25 miles away from left to right, there's about 100 miles on the screen here. So in 100 miles there is about 666 feet of curvature. The tallest building in the Minneapolis skyline is 770 feet. That's the IDS Tower. So this red line should be curved up to the top of the IDS Tower, which it is not. Earth is flat. And this is easy to prove and easy to observe. Are on the road. That is, you see the reflection in the water of the vehicle. Come on. This is called evidence. That's 9.5 miles away. They're not driving on the water, my friends. And you see how they disappear? That's not curvature. I love it. That goes right by that house, too. That was the footage I was looking for. So I'm going to back up here just so you can see it again, where we are. There's Chicago, Shedd Aquarium, to the, what was that called, Photography Point, Peninsula or whatever. 4.21 miles. So from left to right in this picture, It's approximately 5 miles. Doesn't really matter. So what I did was I edited and I kind of made it wider, and I did it again. There's 3 cities there now, but you get the point. What I'm trying to do is zoom out, because if you zoom out, you got to realize the angular size of this city went from the other side of the lake. It's like the size of a pin. So it has to, you have to magnify it. So as you zoom out, we have our 4 miles in the center. There are 5 miles, and then you can keep adding that up, and this is even, we wouldn't even be able to see this with our eyes from the other side of the lake. So what I'm saying is, from left to right, there's many miles that are visible, and it's a perfectly straight line. So I wanted to figure out why videos like this can happen, why people see boats disappearing from the bottom side up. So I set my camera up on a road that is very flat, very long, very straight. And I'm going to show you the footage of me walking about a quarter mile away from my camera and then walking back towards it. First, I'm going to show you zooming out from what we're going to be looking at. Picture the Chicago skyline from across the lake being that car, and just watch as we zoom out how small that gets. So remember our 5 miles left to right. How many miles do you think we can actually see of the shoreline left to right with our own eyes as we zoom out? So I'm going to walk away from the camera 8 times faster than I really did, and we will just watch. Notice as I walk away how I'm shrinking and how my head appears to be going downward. Notice the reflection, and then notice the bottom of my feet not really visible. And probably up to my knees almost, or my waist. Okay, now I turned around and I'm coming back. So since it's clear, observable, and undebatable that we do get a straight line left to right, unlike this red line on your screen, images like this, or this, or this, or this, or videos like this are not happening because of any kind of curvature. They're happening because the ocean has waves and swell, and there's a lot of water in the air. Water is always level and flat at its surface. Okay, it's time for me to demonstrate a universal problem with spheres. They curve uniformly, meaning any point that you're on a sphere would be the top, and then as you look out to the distance, it should drop off, similar to what this board is doing that I made. And I did this to demonstrate something. Okay, off in the far there we have a sailboat, and then this pink styrofoam here is the same height as the mast on that sailboat, and then this is our third sailboat. It doesn't look like a sailboat, it looks like a board, but I made a little slot in there, and my iPhone actually slides right in there, just like that. And then I can slide the board. Now, the reason why I have these here is because I'll show you the camera height at the, it's close enough to the top of that styrofoam. So that other boat, obviously this boat cannot see the other boat till we sail up further, and then it starts to come up over the curvature, right? Okay? There's a reason why I want to show you that. Now here's the problem with spheres. If I measure, let me get my tape measure. From boat to boat, we have about 64 inches or so. 64 inches. So then let's take and go about the center of the two boats, and let's take our third boat and put it over here at 32 inches. Okay, and I can probably show you that. I don't know how if you'll be able to see it. Yeah, you won't be able to see it, but it's right at 32. Now, here's the problem. See the boat? See the boat? And those two boats can't see each other. I can see both those boats, they can't see each other. So, here's the problem. On a sphere, if you're equal distant from a point, like I am with these two boats, the amount of curvature that it would be the same up to that center point where the level is right now that we're looking at, where the bubble is. So we each have 32 inches from that. They can't see each other, but I can see them both. Now, the scale on this doesn't matter, because a sphere is a sphere is a sphere is a sphere. It doesn't matter how big it is, how small it is, how big my toy boats are. It makes no difference. Obviously, the curvature of the Earth, if it were so, it would be not nearly what I have here. This is exaggerated big time. But all we have to do is, the point I'm making is that we have the idea that curvature like this is what's causing boats to disappear as they sail away. Well, that happens in a very short distance. So what I'm saying is that if I can sit right here at our 32 inches, I'm on the same alleged water that they are on, yet do you see in the center, right below the yellow level, what is the ground doing there? See that curve? See that curve? That curve doesn't exist on the Earth. And it doesn't matter the size of the sphere. What I'm saying is that boat can't see that boat because of the curvature. So let's put that as into a real world situation. If I went to the ocean and I looked all the way to my left and I see a boat off in the distance, and then all the way on my right I see another boat off in the distance. Between those boats is much more than 6 miles. And if you were on one of those boats, you might not be able to see the other boat. But I can do a point-to-point visual observation and see that that curve, let me back up, that curve doesn't ever exist. The water follows that, I'm going to probably put it on the bottom of the screen. The water follows like this, like a straight line. And these boats are covered up from each other. What it proves to me is that it's not a logical way of thinking to think that a boat's going to disappear and that you're going to be able to see that disappear, and that's actually curvature, because you would have to be able to see the curvature from this point of view, because from left to right I can see, who knows, 100 miles. And so those boats could be real far from each other and not see each other, but I can see them. And if you've ever been to the ocean, it's a straight, flat line, and you can even take a level, put it on a stand, set it up at the ocean, and you will see that it is a perfectly straight line all the way across
your view.